Hello, my name's Roslyn Massey. I'm a PhD student at Carleton University where I work with the Organic Sensors and Devices Laboratory.
I'm presenting our paper, a comprehensive modelling approach for Bio-EDLC systems, co-authored by the brilliant Dr. Bebe, Dr. Amache and Professor Prakash. The future of energy storage is supercapacitors, small footprint devices with a higher specific energy storage than conventional capacitors and a higher specific power storage than batteries. However, conventional double-layer capacitors rely on high-cost and environmentally damaging materials and device processing. These devices have a double-layer structure of two electrolytes separated by a membrane. Their high capacitance relies on highly ordered ion arrangements called electric double layers at the electrode interface and membrane charge separation. Bulk effects in these devices are minimal, which allows for effective miniaturization. However, modelling these devices is complex, as electrolyte capacitance is a function of frequency. They're commonly modelled with the transmission line model, which is the bottom right figure, which represents frequency dependence as infinite parallel resistor capacitor branches. In order to incorporate DLCs into electronics, their behaviour must be modelled. The simplest modelling method is to use a classical equivalent model. This simplistic model uses parameters extracted directly from impedance spectra and accurately captures conventional capacitor behaviour. However, it fails to model capacitor voltage dependence and complex DLC internal interactions. Despite this, its common usage may make it a useful modelling technique. The Zubieta and two-branch model are derived directly from the transmission line model. The Zubieta model uses multiple resistor-capacitor branches to represent immediate, delayed and long-term DLC interactions, with voltage dependence incorporated into the immediate RC branch. This model has been proven for DLCs, but suffers from limited voltage reliance and an involved parameter extraction process. The two-branch model aims to model internal charge redistribution with only RC branches and claims that their superior method in parameter extraction is not only more robust to noise than the Zubieta model, but performs better. This method has been shown to effectively model DLCs. Organic materials benefit from being lower cost and with higher mechanical flexibility than conventional materials. In addition, complex intra- and intermolecular interactions introduce great versatility, which is the reason why organic DLCs are gaining traction as the next small footprint energy storage device. However, common organic electrolytes such as tetraethylammonium tetrafluoroborate or non-aqueous esters still require highly specialized fabrication environments. Bioelectrolytes are a further improvement on organic materials as they can be processed without a specialized environment, which reduces processing costs, and you end up with a biocompatible final product. As there was no literature on Bio-EDLC modelling techniques, we aimed to determine which DLC modelling technique would best capture the complex Bio-EDLC behaviour. This work will further translate to our emerging organic electrolyte-gated field effect transistor sensors, devices with an analogous sensing mechanism. The Bio-EDLC is two bioelectrolyte gels divided by a semi-permeable membrane. The organic electrolyte-gated FET incorporates a bioelectrolyte into the gate dielectric, where target biomolecules complex with OEGFET top-gate aptamers. This creates a pseudo-resistive membrane that, like the Bio-EDLC, allows charged species to pass. Under applied potential, charged species form electric double layers, while membrane charge separation and dipole orientation increases total capacitance. The OEGFET sensing mechanism correlates current to biomolecule concentration through capacitance influence on the semiconductor channel formation. Capacitances rely on electric double layers and charge separation, hallmarks of DLCs, indicating these devices can be described by transmission line models and other DLC modelling strategies. It's not all good news, as Bio-EDLCs are power range limited to less than 1.5 volts due to the aqueous nature of the bioelectrolyte. However, these complex materials can have very high ionic conductivity, making them effective despite the lower power requirements. These devices also have very low processing and materials costs compared to traditional DLCs and are ecologically sound with a biocompatible and biodegradable final product. They have not been implemented in a commercial technology unlike the DLC. Despite not being flexible or biocompatible, ceramic DLCs have actually been used in emerging wearable systems. Unlike other organic DLCs or conventional DLCs, our devices can be fabricated in oxygenated and humid conditions. We began by fixing copper tape to clean glass slides to form our electrodes, and then we dissolved 1.6 grams of carrageenan, 0.8 grams of PVA, and 1 gram of agarose in 25 milliliters of 1% acetic acid. This was dissolved at 80 degrees C and under constant agitation and allowed to cool down to room temperature in a clean glass mould. The thickness of the gel was found between 300 and 350 microns, and then we spun our separator of cellulose with 125 nanometers of Teflon. Our separator is coated with Teflon to both increase the hydrophobicity and prevent leakage of water across the membrane. Our bioelectrolyte is a composite gel. The gel has a more consistent structure and is robust to leakage and drying when compared to a bioelectrolyte liquid. It also has the added benefit of being a composite material, which has increased conductivity. The carrageenan is the bioelectrolyte, with PVA improving the environmental stability and agarose providing mechanical strength. These materials are simple to prepare and have predictable physical properties. Bio-EDLC data was extracted in 3 different ways. The first was a voltage sweep to determine the breakdown voltage. Following this, we did a constant charge voltage test at 9 volts to determine the rise time. Following this, we actually did the constant charge measurement with a 100 milliamp pulse at 9 volts compliance. The Bio-EDLC was connected in series for this test, and the pulse width was determined by the rise time to be 62 seconds. Following this, we took impedance spectra data over the 40 to 100 Hz range for extracting the classical equivalent parameters. Following this, we simulated the Bio-EDLC in Multisim Suite 14.2, and we were using equivalent circuit models, and those incorporated the extracted parameters. The simulated charge test was performed using the same testing conditions as the real charge test. We compared the Bio-EDLC to the DLC and we discovered significant differences. Most of these were to do with how these devices interacted with traditional capacitor equations. There is a characteristic parameter tau, which is a time constant, and it is the time required for a charging capacitor to reach 63% of its maximum potential. This should be the resistance times by the capacitor of the device. In addition, 5 times by tau should give you the rise time, the time to reach 100% of the maximum potential. This does not hold true for the Bio-EDLC, though it does for the DLC. We've discovered that not only does the Bio-EDLC have a faster charge-discharge time by 10 times than a regular DLC, it does not interact with traditional capacitor equations in the same way a traditional capacitor does. These differences are due to device structure and material choices. DLC capacitance relies on solvent dipole charge localization due to the external field, rather than ion content or solvent choice. Bulk hydrogen bonding to adsorbed water molecules produces lower energy sp3-like bonding structures. The contest between dipole orientation and hydrogen bonded absorption results in capacitance-inducing dipoles distributed in low density. Thermal fluctuations allow more sp3-like adsorbed molecules to switch to dipole orientation, which causes local aggregation and increases the capacitance. The charging time is influenced by the expansion time of these dipole-oriented remains, rather than the device capacitance. We simplified the Bio-EDLC fabrication by using a smooth electrode unlike regular DLCs, which reduces surface area and therefore adsorbed molecule quantity. In addition to the gel matrix and the mildly acidic nature interrupting the hydrogen bonding, this contributes to faster charging, but negatively impacts the capacitance mechanism. Parameters were extracted from the real data for each one of the 3 models. The first was the classical equivalent model, which had the true values extracted directly from the impedance spectra. This demonstrated that the total capacitance of these devices was 70 microfarads, which is comparable to literature DLC values. The values extracted by the Zubieta and 2-branch models resulted in extremely high capacitance values, which are likely not true indicators of the device capacitance, but rather are there to compensate for internal charge redistribution. Another observation of the extracted 2-branch parameters was that the extracted values were greatly affected by the fast rise times, with small differences in charge test results producing large error. Here we have graphed our simulated results alongside our real data. The green is the classical equivalent model. This model had the highest standard error, in addition to not demonstrating any charge redistribution and dramatically over-predicting the maximum voltage. Though this is the most common capacitor modelling method, it is not appropriate for a Bio-EDLC. The two-branch model is graphed in yellow. Though this model had a lower standard error of 1.7%, this simulation fails to reach the maximum voltage. This is likely due to the two-branch parameter extraction method relying heavily on the traditional capacitor equations, which we discovered do not hold true for the Bio-EDLC. The Zubieta model is the most effective at modelling the Bio-EDLC by every measurable metric. It has the least standard error of 0.7%, and it reaches the maximum voltage and accurately mimics the discharge curve. These two parameters, the maximum voltage and discharge curve, are based on the extracted resistance values. The extracted capacitance values are responsible for the charge redistribution and rise time, which the Zubieta model predicts poorly. Despite this, the Zubieta model is the most effective of the three. This was the first attempt at modelling any Bio-EDLC system. We found that the Zubieta model most effectively captured the overall behaviour of the Bio-EDLC with the lowest standard error of 0.7%. Due to the large extracted capacitance value that hindered predictions for charge redistribution and rise time, further investigations into Bio-EDLC modelling will need to tailor the parameter extraction model to the fast charging nature of these devices. However, we believe that this is a promising start and findings will be implemented in analysing OEGFET devices in the future. Due to the potential of our findings, we are hoping to incorporate the Bio-EDLC as a power source in upcoming future organic technologies. Potentially, we could create a fully integrated OEGFET Biosensor chip with these modelled responses. Thank you for logging in!